So now we can start the class. Okay. So first we will recap what we have, what is this week has done. Then we can go for the problem solving. So as we seen in this week, we have seen about what is the different way of we can do the preheat treatment, such as the flame heating, induction heating, infrared heating, and quartz lamp heating. So and their advantages and so on we have seen. As flame heating, here we use a oxyacetylene fuel, oxyacetylene fuel torch we will use. There are three different kind of flames are there based on the ratio of oxygen to fuel ratio, like carburizing flame, neutral flame, and oxidizing flame. Depending on the metal, we can use which are the one, and we use this flame. But this process is the much more cost effective one. But limitation of this one is that we cannot achieve uniform heating and control heating, like at a certain region we want to more heating, certain region we want less, that we cannot achieve. So there is other kind of methods like electrical resistance heating. In this case, by using the resistance principle, we can uh, get the temperature there. So here also we can see the different ways we can achieve this. So here we can see the different ways we can generate at different locations we can vary the temperatures, because it is the electrical resistance we can control the flow of the current. By that we can control the amount of the heat input at given point. But limitation is that it is a bit expensive process compared to the previous one. Next, induction heating and quartz lamp heating. Those are also very control heat input. We can control it, but the problem is that compared to those are expensive and very sensitive to contamination and fragile ones. So based on the applications, we okay. So now we can see some of the have bring some slides. So maybe we can go through those. Mhm. So here is the example of how the induction heating is taking place. Sorry, induction hardening. This is where is the heating one? No, not here. Okay, just leave it. So let's go to the problem solving one. So first one is the what is the primary purpose of preheating before the welding of the steel? What is the reason why we doing the preheating is that to increase the weld speed, to reduce the cooling rate, prevent the hydrogen cracking, increase the hardness in the weld metal, and improve the arc stability. So answer is that reducing the cooling rate. How it reduces is that, so if I give the generally welding, the rapid heating will take place in a fraction of seconds, and the rapid cooling will also take place in a very less time. So here rapid cooling takes place because of the this workpiece acts as a good heat conductor. So heat conduction is directly proportional to the thermal gradient. Suppose if here is the thousands of degrees, it is the here is the room temperature. Because of the higher thermal gradient, heat transfer is much more higher. So we want to reduce this heat transfer. If we increase the base metal temperature to like 200 300 degrees or like that, so thermal the gradient will be reduces. If thermal gradient reduces, the amount of the cooling rate will be reduces. So that is how we can reduce the cooling rate. So answer is the B. So preheating raises the base metal temperature before the welding, which reduces the cooling rate. That allows the hydrogen to diffuse out and decrease the risk of hydrogen induced cracking. That is nothing but a cold cracking. Okay. So next is the which of the following parameters has the uh, least influence on the required preheatment temperature in steel welding. So, which is the least heat treatment, least influence on the preheat treatment requirement? First is the carbon content, carbon equivalent in the steel. So, if the carbon content to affect it, yes, because if the higher carbon content means we have to provide the more amount of the heat input because of the prevention of hardenability. Next is the select section thickness. Yes, if the section thickness is more, the cooling effect will be more because of the metal will much more fastly conduct the material. So that is also not. Next is the welding position, like 1G position, 2G, 3G. I think that those are also we have seen during the our first lecture, right? This is the welding positions. 1G, 2G, 3G, 4G, like horizontal, vertical, flat, horizontal, vertical, overhead, and 5G is the round shape pipe and horizontal pipe and inclined pipe, and 1F, 2F. G means groove welding, F means fillet welding. So based on that, so welding position doesn't affect because it is the we mostly see in the metallurgical point of view. So next is the hydrogen content in the electrode. That is also affected because hydrogen content we don't want to be there. So answer will be the C. So it will be the welding position. Next, what is the carbon equivalent formula? In carbon, it is not only carbon will affect the hardenability. Certain elements will also act as a uh, mm, similar effect on the steels. Okay, those we can calculate by using this carbon equivalent one. What is the percentage of each element? If we put into this formula, that we can get the carbon equivalent. That if the carbon equivalent is higher, though, so it is the higher hardenability. So if higher hardenability means we have to reduce the cooling rate much fast. I mean, we have to slow the cooling rate. So then we have to give the high preheatment treatment requirement. So this is the formula for that one. Next is the preheatment for the welding of low carbon steel. The preheatment generally, I think this is also sir have explained. Uh-huh. I think screenshot is missing. Uh, yeah, it is missing. Okay. For the low carbon steel, if carbon content is less, there is less possibility to become hardened. So always required are required only for the very thick sections, never required, and required only for the submerged arc welding. No, it is be required only for the higher thickness, because then only once the thickness is increases more, then the cooling rate will become much more higher. So in that case only we will try to use this kind of one, because in general if I have a thinner sheets for low carbon steel, it is not required to go for the preheat treatment. Even though if we given, we will give up to 200 degrees or like that, not to more than that. If the carbon content is increasing, the amount of the treatment will be increases much further. I think Sari have already explained, given the for the which carbon content, how much amount of the heat treatment is required, that is given. I think some slide have it. Okay, I think that is missing one. Okay, that's okay. Next is the purpose of the post weld heat treatment. Okay, to increase the what is the purpose of the post weld treatment? To increase the weld metal hardness, relieve the residual stresses and temper martensite, and increase the welding penetration, and reduce the weld metal dilution. Okay, this option C and D are the pre-welding conditions. So after post heat treatment, those will not affect. Increase the weld metal hardness. No, heat treatment will try to reduce the residual stresses. Weld metal hardness we cannot increase by heat treatment. So answer will be the B. So it will reduce the residual stresses, and also if the brittle martensitic phase is there, it may convert into benetic phase or paralytic phase. That is also we can achieve it. Okay, to increase the ductility and toughness. Next is typically stress relieving pre post weld heat treatment for the carbon steel lies in the within the range. This is in the range of 200 to 300, 350 to 450, 550 to 650, 800 to 900. Answer will be C. It will be 500 to 550 to 650 for around 2 hours or like that we will perform it. Okay. Next, preheat treatment required in the high carbon steel. Why we require the preheat treatment is that to mainly to prevent solidification cracking, laminar tearing, formation of the brittle martensitic phase in HZ, and excessive grain growth. So higher carbon content means the martensitic formation will become much more higher, so hardenability will be higher. So that we want to avoid it, so that we will provide the heat treatment. The answer will be the C. So high carbon steels have the high hardenability. The rapid cooling produces the martensitic heat affected zone, which is brittle, prone to cracking. So preheat treatment will slows the cooling rate. So that will prevent the formation of the martensitic phase in a HZ. So preheating in cast iron welding. Yeah. So during the welding of the cast iron, the preheating is mainly used to answer A. Increase the electrical conductivity. That is not the reduce the thermal gradient to prevent the cracking. I think it is a similar question only, just to increase the welding penetration, improve the arc stability. So it will be the reducing the thermal gradient only. So as the carbon content increases, we have to give the more amount of the preheating. So here in this case, it will be reach up to 600 degrees. But in case of low carbon steels, we generally go up to 200 degrees maximum. So as the increase in the carbon content results in requirement of higher preheat treatment temperatures. Okay. Next is the typical holding time for the post weld heat treatment in the steel approximately. So answer will be in general for steel we go for the 650 degrees for the 2 hours. So which is the close to that one is the B. Answer is the So that is 1 hour per 25 thickness. So the common rule for the welding code is that 1 hour per the inch, that is the 25 thickness, to allow the sufficient stress release. To increase the preheat rate temperatures during the weld will be, if we increase the preheat treatment temperature, so what will be the effect? Increase the cooling. I think it is also already seen. So reduce the cooling rate. So answer will be the B. Next, coming to residual stresses. So what is the type of residual stresses? We have the two types of residual stresses. One is macro scale residual stresses. Second is the micro scale. So macro scales one are the much larger scale. It is, as it say, it is developed by inhomogeneous plastic deformation from the external loading, non-uniform heating, or by wearing the chemical diffusion. Suppose like if I hit a workpiece welded or that with hammer, so the surrounding that region will become plastically deformed, and that will generate the macro stresses. Okay, that kind, and or if I heat at a certain location, the that region only will expand and cool down. Because of that, thermal stress, residual stresses will generate in the macro scale level. Okay, next is the micro residual stresses. This is due to formation of the if the metal have a two different kind of phases. Once the heat is heating, so two different phases will have a different kind of thermal expansion and contraction. So based on that, the stresses will generate because of this varying in the volumetric. If certain phase is thermal expansion is more, means it will occupy the more space, but other phase is less thermal expansion, which will restrict it. So based on that, the stresses will generate. Okay, that is the micro stresses. Okay, so in welding, why it is produced is that stresses are prone due to hindrance, contraction, and expansion of the heated metal because of the during the welding process. Only the weld portion only will be reaches the melting point, and it will be varying with the distance. Temperature will be, so because of the difference in uh, temperature at different location, the expansion rate also will be changes that generates the residual stresses. Next is the phase transformation. If so, some phase is changing from one to other, if that phase is having the different volumetric expansion, that will generate the more amount of the stresses, and restraint of the thermal expansion and contraction offered by other parts of the structures. That means if I doing the welding, and the weld plates are uh, fixed in a clamp. In that case, the during the welding process, because of the thermal expansion, the weld plates cannot be grow. I mean, expand further because of the clamps. So because of that, it will generate the some other residual stresses. Okay. So based on this, we can see some of the problems. Then we can discuss further. So nature of after welding and cooling to the room temperature, the weld metal generally experiences. Weld metal will be, which kind of stresses will be there? Compressive stresses, tensile, zero stresses, or alternating stresses. I think this also sir have already touched. Yeah, here. So during heating time, you can see here. Here is a positive is the tensile test, tensile stresses, and negative is the compressive stresses. Okay, because of during heating, it is started expanding. So the tensile test tensile stresses will be generated at the weld bead. But once the during the cooling phase, this will be cools fast compared to the surrounding. So because of that, compression stress will sorry during during cooling it will be the, here is the tensile test will be stresses will be generated here, and compressive stress will be generated at the base material. Why is that? uh, During cooling phase this will be cool much faster, so which will have a this kind of profile. I think opposite will be true for the during the heating phase. Heating phase will be stresses will be follow this kind of pattern. Okay, so it will be the answer will be the tensile stress. Okay. So answer will be the molten weld will cools and solidify in contrast, uh, in context, but restrained by surrounding base material. The restraint produces the tensile residual stresses in weld metal, balancing the compressive stress in a adjacent region. Okay, just here you can see the profile. Okay, next. In typical butt weld plate, the residual stress distribution along the weld direction. Tensile in the weld, compression are far from the weld. You can see same thing. I think this is the profile only they are asking. So here is the tensile at the center, and far from it will be the compression. Okay. Compressive at the weld and tensile at the far. This is the true while heating condition. This is true while cooling condition, because cooling is the later one coming. So answer will be the A. And 0 everywhere, that is also not true, and alternative random, that is also not true. So it will be the high tensile stress near the welding and compressive stresses at the away from the weld. Next is the residual tensile stresses in weld joints mainly increases the risk of which kind of problems? Fatigue failure or brittle fracture, improves the ductility, increases the corrosion resistance and grain refinement. Answer will be the fatigue failure. Okay. Residual tensile stresses added to apply the applied stresses, so that will be increase. So it will be already compared to already existing stresses. It will be increased further, so that will reduce the fatigue cracking, brittle fracture, and stress corrosion cracking. Which of the following techniques is commonly used to measure the residual stresses in weld structures? Okay, I think we have come to measurement of the residual stresses. So which kind of methods we can use? One is the brittle coat method. Second one is the photo stress method. Third is the strain gauge method. Okay. So in brittle coat method, what we do is that the sample surface first we clean with the emery paper, then we apply the alumina paste, aluminum coating. Then after we put a some brittle coating on it. So brittle coating will not have any expansion, right? Brittle means it will fracture immediately. So after that we will make a 3 millimeters diameter hole there. Because of that hole the stress relieving will takes place, that will changes the uh, workpiece in microstructure. I mean it will stress relieving will takes place, that will as the coating has the brittle property, so wherever the compaction and expansion takes place, there the this brittle coating will be started showing the fractures. There we can find out the stress amount of the stress level. This is called as a brittle coating method. Similarly, that photo one also, photo stress method, it is also similar to that one, but instead of the brittle coating, we put a some polymeric uh, coating which reflects this polarized light. Based on the fringes we can see on the visual screen, based on that we can find out the what kind of stresses are present there. Okay. So some of the other methods also there, like which kind of stress, ultrasonic X-ray diffraction. If you do the XRD, so if the residual stresses are there, the peaks will be shifted from exact location. From like if in idle, if a material having the XRD peaks in here is the 2 theta, certain like here is the suppose assume 20 degrees, and some other peak is at 60 degrees or like that. In ideal without any stresses. If there is the residual stresses, this may peaks may be shifted to 22 or 63 or like that. It will be shifted. Based on that, we can find out the how much amount of the residual stresses are there. So X-ray diffraction method measures the residual stresses by detecting the lattice strain changes in the crystal material. Other metal including hole drilling and downturn diffraction. Okay, which of the following method is most effective in reducing the residual stresses in weld joint? Answer will be by increasing the weld speed, no post weld treatment, increase the electrode diameter using the higher weld current. Answer will be the post weld heat treatment. That will simply, if we increase the temperature, so the readjustment of the microstructure will take place, which will reduce the stresses. Okay, next, distortion due to residual stresses. Residual stresses in welding often leads to improved weld strength, distortion and dimensional inaccuracy, increasing the melting temperature, reducing the weld penetration. Answer will be B. Uneven residual stresses causes distortion, including angular distortion, buckling, warping, and longitudinal shrinking. The magnitude of residual stresses in welded joints can be reached approximately half of the yield strength, equivalent to yield strength of the material, twice the yield strength of the material, 0. Answer will be the half of the yield strength of the material. Residual stresses produced during the welding can reach the value close to the yield strength of the material because of the plastic deformation occurs during the thermal contraction. Next, the preheating the base material before welding helps in reducing the residual stresses by increasing the hardness, increasing the cool rate, reducing the temperature gradient during the welding, and increasing the weld penetration. Answer will be C, reducing the temperature gradient during the welding. So preheat treatment reduces the temperature difference between the weld and surrounding materials. That's it will lowers the thermal gradient, so that the cooling rate will be reduces. That reduces the residual stresses and distortion. Okay. Okay, next, which of the welding practice helps to minimize the residual stresses and distortion in the large welding structures? So answer will be random welding sequence, systematic welding sequence, weld only from the one side, or user thicker electrodes. I think this is sir have taught. So welding procedures and sequence. In this one, we can see where is that sequences. Yeah, here. So proper backstep welding and skip welding processes, we can reduces the uh, amount of the residual stresses in a given welding bead. Okay. Answer will be symmetrical welding sequence. So next is the thermal. The principle of causes the residual stresses in the weld joint is uh, answer one A, change in the electrode polarity. B, non-uniform thermal expansion and contraction during the welding. C, oxidation of the weld metal. D, difference in the filler metal composition. Primary cause of the residual stresses due to non-uniform thermal expansion and contraction during the welding. As we seen here, so here you can see during the welding process, here is the higher heat temperature is there, because of that volumetric expansion will be more, and here will be the low temperature. So the change in the volumetric expansion in a given workpiece results in the residual stresses. So answer will be the B, non-uniform thermal expansion. Next is the residual tensile stresses develops in the weld metal mainly due to excessive arc voltage, restricted contraction of the weld metal during the cooling, diffusion of the alloying elements, increase in the electrical resistance. So it is mainly due to thermal expansion and contraction that results in the change in change in the volumetric expansion that results in the residual stresses. As the weld metal cools, it tries to shrink. However, the surrounding base metal restricts its contraction, resulting in the tensile residual stresses in the weld zone. So as we seen here, so here is the weld bead location. Here we can see the tensile residual stresses followed by the compression stresses in the uh, workpiece. Similarly, in transverse direction also, at the edges we can see the compression stresses here and here, and enter the weld bead we can see the mainly tensile stresses. Next, in the steels, residual stresses may also arise due to a phase transformation during the cooling, increasing the arc length, electrode coating reactions, the flux melting. So as a steels, there is a as increasing the temperature, the phase will be changes from parallel to a gamma phase and so on, austenitic phase and so on. So during the phase transformation, the volumetric change will occurs that will generates the lot of stresses like martensitic phase, from converting from austenitic phase to martensitic phase. Is much more martensitic phase has the much more volume compared to the austenitic phase. So once it is because of the rapid cooling, if the martensitic phase is formed, it will occupy the more volume of the space, but the surrounding base metal will try to restrict it, so that generates the stresses in the material. So answer will be the phase transformation. So this we can avoid by providing the preheat treatment, so that the formation of the martensitic phase we can restrict it. The residual stresses in the welding structure increases with. So A answer will be decreasing the weld decreasing the weld joint to restraint. B, increasing the weld joint restraint, decreasing the weld current, and increasing the arc length. So residual stresses in welding comes with mainly due to three reasons. Okay, one is that, yeah, here, so hindering and contraction and expansion of the heating material, that is mechanical stresses like and next is the phase transformation. Third is the restriction of the workpiece during the thermal expansion phase. Okay, so here is the if we decrease the welding restriction, the residual stresses will be reduces. So answer A is also answer is not. Answer B, increasing the joint restraint. So then the residual stresses will increases. Okay, and decreasing the weld current, that doesn't affect, and increase the arc length, that is also not affect. So if the joint has a high restraint it cannot be deformed freely during the heating and cooling. That restricts the prevents the stress relaxation, results in the higher residual stresses. Next, residual stresses are generally higher in welding of thinner plates, thicker plates, powder metallurgical parts, and composite metals. Answer will be thicker plates. Why? Because if the plate thickness is higher, it will act as a very cooling rate will become much more higher because of the higher thermal quenching effect. If it is thinner plate means it will base metal also will be heating up very fastly, so that the cooling rate from the molten pool to base metal will become slow. But if it is a thicker plate means the cooling rate will become much more faster because of the amount of the heat can be absorbed by the workpiece is much more higher. So that if faster cooling means more residual stresses. Okay, thicker section have the higher thermal gradients and greater resistance that makes it difficult to stress or to relax, which leads to higher residual stresses. The residual stresses can develop when entire workpiece is heated uniformly. Localized heating occurs during the welding done at the lower current, welding done at in the flat position. Answer will be just as previously we discussed, it is the localized heating. Welding produces the localized heating that causes the expansion in bone in the small region. When this region cools, contracts, the surrounding cooling material restricts the movement, producing the residual stresses. Okay. One cause of the residual stresses forms in the weld metal is solution shrinking of the molten metal, increasing the electrical resistance, magnetic effects in the welding, and flux entrapment. I think it is also similar type of question only. Solution shrinking of the molten metal. Next, residual stresses in welding are strongly influenced by uniform cooling rate throughout the workpiece, differential cooling rate between the weld and base material, electrode diameter only, sealing gas composition. I think it is also just to rephrase the question only because of the difference in the cooling rate between the weld and base material uh, generates the because of the thermal gradient it changes the residual stresses generated. The weld region cools at the different rate compared to the surrounding metal. That uneven contraction generates the internal stresses after cooling. Increasing the heat input during the welding generally leads to reduce the residual stresses, increase the residual stresses due to the large heated zones, no change in the residual stresses, or elimination of the residual stresses. Once we increase the high heat input, the if heat input is more, so the thermal gradient will be also increases. So if the thermal gradient increases, the contraction and expansion will be much more higher. That results in the higher residual stresses. Higher input creates the larger thermal gradients, which widens the heat affected zones, which increases the thermal strain and residual stresses. Okay, which of the following conditions most promotes the residual stress development during the welding? Free expansion of the welding parts, rigid clamp of the components, uniform heating of in the furnace, and slow cooling in furnace. Answer will be rigid clamping and components. As you see, the three factors which will affect the one is the hindering of the contraction and expansion, phase transformation, and restriction of the thermal expansion. So next, which of the following technique is the non-destructive method to measure the residual stresses in weld joint? I think it is we have seen it is the XRD. As the XRD method measures the lattice strain in crystal materials and calculate the residual stresses using the elastic contraction. It is a non-destructive test. Okay. Next is the which of the following residual stress measurement technique is a destructive one? Answer A. Neutron diffraction, ultrasonic testing, sectioning method, and magnetic Barkowski noise method. Answer will be sectioning method. In sectioning method, weld component is cut into small pieces. The release of the residual stresses causes deformation, which measure to estimate the original stress distribution. Okay. Okay. Next, the hole drilling method measures the residual stresses by. Okay. Measure the thermal expansion, measure the strain relaxation after drilling a small hole, measures the change in the hardness, observes the weld bit geometry. So hole drilling method, as we seen here, hole drilling method. Once we drill the hole, but after that we see the relaxation after the uh, strain relaxation after the drilling the hole. Okay, small hole is drilled at the measured point, causes the local stress relaxation. The strain gauge around the hole measures the released strain, which is used to calculate the residual stresses. Okay. Compared to the X-ray diffraction and neutron diffraction has the advantage of low cost, measure stress deep inside the thick plate, faster measurement time, and simplest equipment. As a XRD only can measure the surface stresses. Neutron have the high penetration depth which allow to measure the internal residual stresses deep inside the weld metal, unlike XRD which measures the surface stresses. Okay. In the layer removal method, the residual stresses determined by measuring hardness variation, measuring deformation after the successive removal of the thin layer, measuring temperature change, measuring weld beat width. In this method, answer will be B. The measuring deformation after successive removal of a thin layer. Okay, it is the layer method. In this method, thin layer of the metal are gradually removed, causes stress redistribution. The resulting deformation strain changes used to calculate the residual stresses. Okay, the the magnetic Barkhouse nose method mainly applicable for the measuring residual stresses in ceramic metal, non-ferrous metal, ferromagnetic metals, and polymers. Answer will be as it is magnetic, we require the ferromagnetic materials. MBN works only in the ferromagnetic materials. Changing the residual stresses affect the magnetic domain movement, produces the detectable noise signal. The ultrasonic method for the residual stresses measures on based on the plastic deformation of the material, change in the ultrasonic wave velocity due to the stress, thermal effects, thermal expansion coefficient, and chemical composition change. Answer will be B. Change in the ultrasonic wave velocity due to the stresses. Okay. Residual stresses alters the electric properties of the material, elastic properties of the material, affects the velocity of the ultrasonic waves. Thus, phenomena known as a acoustic elastic effect. Which of the technique is mostly suitable for the measuring surface residual stresses in weld component? Okay, section method, XRD, layer removal, neutron reflection. Section method is a much more tedious process as we have to cut each layer and measuring it, and it is also destructive process. While X-ray diffraction is a we can measure in a fraction of a few minutes, and layer removal also it is also a tedious process. Neutron diffraction it is not destructive, but it is a much more expensive process. So X-ray diffraction is the widely used for the surface stresses measurement because X-rays have a limited penetration depth, typically few micrometers. Okay. The strain gauge is commonly used in residual stresses measurement in option A, X-ray diffraction, option B, hole drilling method, option C, neutron diffraction method, option D, magnetic percussion method. Option answer B, because that is the only destructive test. Remaining all are non-destructive tests. In the as we see here, this kind of strain gauges we use two. One is the uniaxial one, and the other one is the. So this strain gauges we can use to measure the strains. Okay, the hole drilling method, strain gauges is placed around the hole to measure the strain releases when residual stresses are released, allowing to calculate the original stresses. Next, in strain relaxation technique, the measuring residual stresses in the weld mates, the stress is determined by A. Measuring the hardness changes, B. Measuring the strain release after material removal, measuring the temperature range during the welding, measuring the weld bead's geometry. Answer will be to measure the strain release after the material removal. So in strain relaxation methods, a portion of the material is measured and section are drilled, which results in locking the residual stresses. The results strain changes is measured and used to calculate the original stress. The brittle coating method detects the residual stresses by observing magnetic domain change, crack pattern formed in the brittle coating, change in the electric resistance, change in the weld color. So answer will be as we seen here, change in the brittle coating, cracks in the brittle coating. We can see crack pattern in the brittle coating, which will use to measure the residual stresses. The brittle coating is appeared on the surface when residual stresses are released or applied stresses are occurred. The coating cracks along the line of the maximum tensile strain, that revealing the stress pattern. Okay. In brittle coating method, the cracks generally forms parallel to the maximum tensile stress, perpendicular to the maximum tensile stress, parallel to the compressive stress, randomly. Answer will be perpendicular to the maximum tensile stresses. The brittle coating fails in tensile, so the cracks appear perpendicular to the direction of the maximum tensile stresses. Okay. Next, the first photo stress method for the residual stresses measurement is based on plastic deformation, optical birefringing under the polarized light, magnetic flux leakage, ultrasonic wave reflections. Answer will be the 4B, optical birefringence under polarized light. The photostress method uses the photoelastic coating under the polarized light. The stress produced bright fringes forms color fringes patterns that corresponding to the stress magnitude. You can see here we have the workpiece. Here is the screen where we can see the fringes. Here the polarized light will fall onto the workpiece and it will reflect, and here we can see the patterns. Based on the patterns we can find out the residual stresses. Advantage of the photo stress method. The photo stress method is particularly useful because option A measures only compressive stresses, provides full field stress distribution, requires the destructive testing. D works only in the high temperature. So what is the major advantage is that provides the full field stress distribution. Answer B. Okay. The photo stress technique gives a full field visualization of the stress distribution over the surface instead of the measuring stresses at only one point. Okay, next question. The residual stress measurement using the strain gauges. The strain gauge primarily measures temperature change, electric resistance change due to strain, magnetic flux variation, acoustic emission. Answer will be strain gauge is a piezoelectric material. So once a change in the strain, which results in the change in the its electric resistance. Strain gauge works on the electric resistance changes when conductor is strained. The change in the resistance correspond to the strain released after the stress relaxation. Okay, next. In the hole drilling method, combined with the strain gauges, the residual stresses are determined by observing the crack propagation, measuring the strain release after drilling hole, a small hole, measuring the weld penetration, measuring the electric current flow. Answer will be B. First option is suited when we do the brittle coating condition, but when we use the strain gauges, we measure the strain release uh, in the strain gauges. Okay, during the drilling of the small hole, relieves the localized residual stresses, causes the deformation. The strain gauge placed around the hole measures the strain, which is used to calculate the residual stresses. The brittle coating method is mainly suited for detecting the high strain regions qualitatively, measuring the exact numerical stress value, C, measuring the subsurface stresses, D, Measuring the residual stresses in the ceramics only. Option will be A. So the brittle coating method mainly identifies the high strain areas and stress concentration, but it is not very precise for the exact stress magnitude measurement. Okay. Next, in strain relaxation techniques, the residual stress measurement requires uniform heating of the specimen, releasing the locked stresses by machining or drilling, increasing the welding current, decooling the weld slowly. Answer will be B. We have to drill the hole so that the stress relaxation will be takes place. This technique relies on the releasing of the locked stresses by removing the material by using drilling, machining or sectioning. The result in strain changes reveals the residual stresses magnitude. Which of the following methods directly measures the stress release during the residual stress relaxation? Answer will be A. Photo stress method, B. Brittle coat method, C. Strain gauge method, D. Dye penetration testing. Answer will be C. Strain gauge method. The strain gauge directly measures the strain when residual stresses are released. Other methods like brittle coating and photo stress method mainly uses the visual stress distribution. Okay. Next, coming to the final uh, chapter, that is the residual stress control. Okay, the main objective of the controlling the residual stresses in weld structure is due to increase the weld speed, reduce the distortion and prevent the cracking, increase the weld penetration, improve the electric conductivity. So answer will be reduce the distortion and prevent the cracking. Okay, residual stresses can lead to distortion and fatigue failure and cracking. Controlling them prevents the improves the structure integrity and dimensional accuracy and service life of the weld component. The preheating the base material before the welding helps to control the residual stresses primarily by how the preheating helps, that is I think we have already seen it is by reducing the thermal conductivity. So option A will be increasing the weld hardness, B reducing the temperature gradient during the welding, C increasing the melting temperature, D increasing the arc voltage. Answer will be B. Preheating reduces the temperature difference between the weld metal and base material, which decreases the thermal gradient and thermal contraction stresses. Next, which welding practice is most effective in reducing the residual stresses and distortion in the large structures? Option A, random welding sequence, systematic welding sequence, weld only from one side using higher welding. So answer will be here. You can see how we can reduce the stress. See that there are different methods. One is the pinning, vibration stress relief, thermal treatment, thermomechanical treatment, weld procedure sequence, and metal design and considerations. So pinning means we are hitting with the hammer on the surface of the weld joint so that stress relieving takes place. So, but we have we should if we shouldn't give more amount of the heating, so otherwise it may get the cold working and work become much more harder. So we have to do in a certain way. Next is the vibration stress relief. This is the we are providing the it to natural frequencies vibrations that will release the stresses in the material and improves the resistance to brittle fracture. Okay. Next is the thermal treatment. In this one, uh, we gives the post heat treatment to so that the stress relieving will takes place. Constant consistency of the heating of the weld structure uniformly to the suitable temperature, holding then cooling uniformly. Okay. Next is the, so how we do that? It is the 650 degrees for the 2 hours for the 25 mm thickness. The amount of the, if the thickness is increases in the 25, we have to increase the number of hours. Okay. So it is the variation of the temperatures with the change in the residual stresses. Okay. If we, and next thermomechanical treatment. In this one, we provide the technique aim to use to thermal expansion to prevent the mechanical forces that step up the contracting residual stresses system and cancelling the original stresses developed during the welding. Okay, how it works is that if the thermal stresses are in the weld bead look like this way, we provide the thermal heat treatment in opposite of this one, so that these two will be cancelled out and reduces the residual stresses. Okay. Two bands of heat move tandem along the longitudinal direction of the weld. This results in thermal expansion of the base material. The temperature is usually lower, hence improvement to the mechanical. This increases the metallurgical properties. Like this, we can provide the two bands of heating to the base material so that these two stresses will become compensated out. Next is the welder procedure and sequencing, like a weld procedure like backstep welding and skip welding, and weld sequencing to ensure the unstrained transition shrinking. Okay, so here answer will be the systematic weld sequencing. Next is that the post weld treatment, the most commonly used method for the relieving the residual stresses in the weld joints, increasing the weld reinforcement. B, post weld heat treatment, increasing the weld speed using the thicker electrodes. Answer will be post weld heat treatment. So post weld heat treatment allows the material to relax through the creep and plastic deformation at elevated temperatures, significantly reducing the residual stresses. The mechanical stress relief methods for the weld mate including vibration stress relief, increasing the weld current, reducing the electrode diameter, increasing the arc length. Answer will be vibration stress relief. As we seen here, weld structure is subject to vibration for the stress relieving using the oscillation or rotating waves generated by mechanical couple to part to be stress relieved. Okay. Then structure vibrates at the one of the natural frequencies. It can reduce the magnitude of the peak stresses and improves the resistance to brittle fracture and does not alter the metallurgical structure of the weld and mechanical properties. So answer will be A. Vibration stress relief uses the control vibrations to redistribution and reduce the residual stresses in the welded structures. Okay. Pinning of the weld bead helps to control the residual stresses by increasing the weld penetration, introducing the compressive stresses on the weld surface, increasing the heat input, and increasing the cool rate. Answer will be B. Increasing the introducing the compressive stresses on the weld surface. Okay. Pinning involves hammering the weld bead, which plastically deforms the surface and introduces the compressive stresses that countering the tensile residual stresses. Okay. Lower heat input during the weld generally results in higher residual stresses, lower residual stresses due to reduced in the thermal gradient, no effect in the residual stresses, increasing the weld metal hardness only. So answer will be B. As we seen, if the thermal gradient is increases, if the thermal residual stresses, if the thermal gradient decreases, the amount of the residual stresses is reduces. One way is that if the heat input is high, we have to provide the preheat treatment so that residual stresses will be thermal gradient will be low. Or if you provide the less heat input, then also thermal gradient will be less, so that will reduce the heat of residual stresses. Okay. Lowering the heat input reduces the size of the heat affected zone and the thermal gradients, thereby decreasing the magnitude of residual stresses. Okay. Which of the following joint design helps to minimize the residual stresses in the weldments? Okay. Answer A. Highly restrained joints. Joints allow the free contraction and thick multipass joints and deep penetration welds only. Answer will be B. Joint allowing the free contraction. As we seen, residual stresses generates by restriction of the joints also. So if we joints are freely moving, so the amount of the residual stresses are low. The designing joints that allow free expansion and contraction reduces the mechanical restraint and helps to prevent the high residual stress development. Okay. Next, backstep in welding technique. The weld is deposited. The In backstep welding technique, the weld is deposited continuously in the forward direction, a short segment opposite to the overall weld direction, only one side of the joint and randomly across the joint. Answer will be B. In short segments opposite to the overall weld directions. Okay. Backstep welding involves deposition of the weld segments opposite to the general welding direction, which reduces the heat accumulation and residual stresses. Okay. Next, excessive clamping during the welding generally leads to reducing the residual stresses, increasing the residual stresses due to uh, restraint, no change in the residual stresses, improving the weld penetration. Answer will be B. Increasing the residual stresses due to restraint. Okay. So rigid clamping prevents the free contraction during the cooling, increasing the restraint and thereby increasing the residual stresses in the weld joint.